Hello everyone, welcome back to Z Physics. Today we are going to be doing some A-level physics question practice. First off, just a couple of notes on how to actually use this video. First off, it is vital that you guys attempt the questions, and you're going to find links to each question in the description of this video. So please attempt those questions. After you've attempted those questions, please mark them using a combination of the mark schemes and these videos. And then if you really want that 8-star, you should try and do all the questions on that particular topic. For instance, all the questions that you can find on electric fields within your exam board. I'm going to be doing the questions on the OCR Physics A examination. However, the physics behind them is very much transferable to all physics exam boards. Please note, however, that these are not official solutions, and if you're seeking official solutions and the papers with their official mark schemes, please visit the OCR website, and I've also included a link to the OCR website in the description below. Okay, well, without any further ado, let's get started with our first question in electric fields. The first bit of this OCR Physics A 2011 question is to define electric field strength. So the field strength is defined as the electrical force. We can also just write the force per unit charge. So the force per unit charge. We know that because electric field strength, the equation for it, you don't have to write that in an exam, but the equation for it is that the electric field strength is equal to that electrical force divided by the charge, hence force per unit charge, if you've ever forgotten that definition. Okay, so for part C, we have a beam of electron which enters the plates at right angles, and the horizontal velocity of the electrons is 4 times 10 to the power of 7 meters per second. The path of the electrons is shown. Okay, we have some dimensions. What I want us to do for the first part is to draw an arrow on the figure to show the direction of the acceleration of an electron at point P. So if we had an electron at point P, this would be, the electron will be repelled by the plate A. The reason for that is because this plate over here is negative, so this means that an electron at P will be repelled because negative and negative repel, but it will also be attracted towards the positive plate because positive and negative attract. So this means that there will be a resultant force acting on P, which will be straight down, and the acceleration will be in the same direction as the force, which is vertically downwards. Okay, so for part 2, we need to show that the acceleration of an electron between those two plates is about 1 times 10 to the power of 16 meters per second squared. That is a huge acceleration. Anyways, let's get down to work. So we know that the acceleration will be determined by the electrical force, and the electrical force is equal to E times Q. If you're wondering where I got that from, just look over here. The electric field strength is force divided by charge, hence the force is going to be the electric field strength multiplied by the charge. In this case, that would just be the electron charge, but we'll get to it. Now, the force is equal to ma, that's the resultant force. Let's assume that's the only force acting on this. And this will be equal to the electric field. However, this is parallel plates, so the electric field will be equal to V over D multiplied by the charge. This would mean that the acceleration will be given by the following expression: V times Q divided by D times M. And now we're ready to essentially plug in some numbers. So we know that the voltage between the plates is 3.4 kilovolts, so that's 3,400 volts. So I can just write this down over here, 3,400. Because we're dealing with the acceleration of an electron, the charge is just the elementary charge, 1.6 times 10 to the power of minus 19. We're going to divide that by the distance between the plates, which is, there's actual typo in here, and because notice that we're given 0.05 centimeters and 0.05 meters here, so let me just correct that. This over here should just say 0.05 meters. So the diagram is correct. Okay, well, we're going to divide that by d, which is 0.05, like so. We'll also be multiplying this by the mass of an electron, which is 9.11 times 10 to the power of minus 31. And if we put that into a scientific calculator, we are going to get 1.19 times 10 to the power of 16 meters per second squared, which up to one significant figure is about 1 times 10 to the power of 16 meters per second squared. Hey guys, next part, calculate the time taken for the electron on entering the plates to reach P. Now, a couple of really important bits. Number one, the horizontal velocity of the electron is completely unaffected by the force which acts on it, because the force is acting at right angles to the motion. Hence, there's no work which is being done in the horizontal direction, only in the vertical. So this means that the horizontal speed will remain the same. Therefore, we can use simply the fact that time will be equal to distance divided by the speed. So our distance up to point P is going to be half of 0.08, so it's going to be 0.04. We're going to be dividing that by the horizontal speed, which is 4.0 times 10 to the power of 7. So it's about 10 to the power of minus 2 here. Those are going to cancel, and that will leave us with 1.0 times 10 to the power of minus 9 seconds. So that's a pretty short time. Let's have a look at part 4 next. Okay, for part 4, we need to show that the vertical velocity of the electron at point P is about 1.2 times 10 to the power of 7 meters per second. Vertically, this electron at P will be accelerating because it is experiencing a force which is going downwards. So we can no longer just use distance is equal to speed times time. We're going to have to use these Suvat equations because there will be a constant acceleration in between those plates. So given that, we need to find the final velocity, and we have the time, and we also have the acceleration up here. I'm just going to use the fact that final velocity is equal to initial velocity plus at. Once again, v over here is our final velocity, u is our initial velocity, and all of this, by the way, is in the y plane, and a is the acceleration, t is the time. The initial velocity in the y plane is 0. We can see that the electron is just going in purely horizontally. So this equation will then turn into v is equal to a times t. So this will be equal to the acceleration. I'm going to use the more precise value that we got for the acceleration, which was 1.19 times 10 to the power of 16. So 1.19 times 10 to the power of 16 multiplied by the time, which is 1.0 times 10 to the power of minus 9, and this will give us the answer about 1.19 times 10 to the 7 meters per second, which is approximately equal up to two significant figures to 1.2 times 10 to the power of 7 meters per second. So for part 5, we want to calculate the magnitude of the resultant velocity of the electron at point P. So you can see that I've drawn over here a couple of vectors. At point P, the electron is going to have two velocities. It's going to have a horizontal velocity, which is 4 times 10 to the 7, and a vertical velocity, which we've just calculated at 1.2 times 10 to the power of 7 meters per second. So all we need to do really is just add up those two vectors. The way we do that is with the tip to tail rule, then using Pythagoras' theorem for the magnitude. So the resultant velocity, let's call that v, and let me just choose a smaller pen to write with. So v squared is going to equal to 4.0 times 10 to the 7 squared plus 1.2 times 10 to the power of 7. All of this is squared, and remember that we need to square root this expression, so v will be equal to the square root of 4.0 times 10 to the power of 7 brackets, all of this is squared, plus open up bracket 1.2 times 10 to the power of 7 squared. Carefully inputting this into a calculator, we're going to get a magnitude for the velocity to be 4.2 times 10 to the power of 7 meters per second. For part 6, it's actually an easier part. All we need to do is calculate the kinetic energy of the electron. Nothing fancy, we know its speed already, so remember the kinetic energy, let's call that Ek, is equal to a half mv squared, so this will be equal to a half times 9.11 times 10 to the power of minus 31 multiplied by the velocity squared, so it's going to be 4.2 times 10 to the 7. All of this is squared. Now let's go through the last question. On figure 3.3, sketch the variation of the kinetic energy of the electron with the horizontal distance traveled as it travels through the electric field and beyond. No calculations are required. You can see that I've underlined some of the key terms over here. So through the electric field, what's going to be happening to the kinetic energy? What's going to be happening to the kinetic energy, if anything, beyond? And we shouldn't be doing any calculations. Unfortunately, even though we really like doing calculations, but just this time, let's try and do that without any calculations. So first off, the electron will actually arrive in the region between the plates with some kinetic energy. The reason for that is because the electron already arrives, with a pretty high speed of 4.0 times 10 to the power of 7 meters per second. As it arrives, that kinetic energy is going to rise to some other value as the electron picks up speed up to 0.08. The question is, how is it going to rise? Is it going to be linear, or is it going to be in any other fashion? It would definitely not be linear because the kinetic energy is proportional to v squared. And if we think about it, v will be proportional to that distance, as we've just calculated, so it will be a non-linear relationship. So the kinetic energy is going to rise non-linearly in a steeper fashion, just like this. Let me just draw this a little bit more carefully, like that. So it will be increasing, getting a bit steeper, like that. Now at 0.08 and beyond, the electron will have already essentially escaped, and after it escapes, there are no forces acting on this electron. Remember, for the purposes of this question, we're ignoring the gravitational force or any other forces. Therefore, the kinetic energy should remain constant after this. I'm just going to use a ruler to draw this quite carefully. Now, when I teach this question in class, normally I get the question, how exactly do we know that the kinetic energy is going to rise non-linearly? And if you're still not satisfied with my explanation, you can have a look at the maths, and just in the horizontal direction, for instance, or actually in the vertical direction, the kinetic energy is in all directions. Actually, the kinetic energy is equal to a half mv squared. Therefore, the kinetic energy will be half m a times t. We've already done this earlier in the question, and we can see that the kinetic energy is going to be proportional to the acceleration squared, which is vq over dm, and multiply by the time. And we found the time by getting the distance, the horizontal distance x. So remember how we divided 0.04 by the horizontal component of the velocity. So the kinetic energy, turns out, is going to be proportional to x squared. Okay, well, let's have a look at the next question. Okay guys, on to our next question. Once again, you can find the questions in the description of this video. This one is from OCR Physics A from 2013. Figure 2.1 shows two identical negatively charged conducting spheres. The spheres are tiny and each is suspended from a nylon thread. Each sphere has a mass of 6.5 × 10⁻⁵ kg. We're also given the charge and the separation between the spheres. For the first part, we need to calculate the number of excess electrons on the surface of each sphere. So remember, the way we calculate excess electrons is, or the number of excess electrons would be that they are equal to the charge, the total charge divided by the electron charge. So the charge on each of those spheres is either plus or minus 2.8 times 10 to the power of -9. And we're going to be dividing that by the electron charge, which is 1.6 times 10 to the power of -19. And if we put that into a calculator, up to two significant figures, we're going to get 1.8 times 10 to the power of 10 electrons. This is quite a large number, so it's probably correct. Right, moving on to the next one. Calculate the repulsive electrical force acting on this sphere. Because we're given the distance between the two charges as well, 2 centimeters, we can calculate this directly using Coulomb's law. So the electrical force is going to be given by the product of the charges. So our equation is QQ over 4 pi epsilon naught r squared. The two charges are the same in this case, so we can just square this value essentially with a little minus sign. So this will be equal to minus 2.8 times 10 to the power of -9, and all of this is squared. That's going to give us a positive answer, of course. We're going to be dividing that by 4 pi epsilon naught, which is 8.85 times 10 to the power of -12, multiplied by the distance squared. Let's not forget to both square the distance and also change that from centimeters to meters. So it's going to be 2.0 times 10 to the power of -2, all of it squared. And this will give us 1.8 times 10 to the power of -4 newtons. Okay, so for part C, each sphere is in equilibrium and experiences 3 forces. So one of the spheres acting on each sphere is the electrical force, the other 2 forces. You can see that I've actually drawn those forces. We have the electrical force, which is essentially repelling the 2 charges. We also have the weight, which is acting straight down, and we also have the tension, which is acting at an angle theta to the vertical. So the weight is one of the forces, the other one is the force of tension. Right, part 2, use your knowledge of vectors to determine the angle theta made by each thread with the vertical. Now this is really important because this is balanced. So because the sphere is in equilibrium, as it says right over here, we're gonna need to have a balance of forces. It means that the vertical component of the tension will be equal to the weight in order to keep this sphere in balance. Now the weight is, we can calculate that pretty easily. In fact, let's just do that really quickly over here. So the weight is equal to mg. Please don't use just the mass. We're given the mass, which is 6.5 times 10 to the power of -5. We're going to multiply this by 9.81. I'm going to get that the weight is equal to 6.38 times 10 to the power of -4 newtons. So this component of the tension going upwards is going to be 6.38 times 10 to the power of -4 newtons. we know what this component is. We actually already know what the horizontal component is because we calculated that up to two significant figures over here being 1.8 times 10 to the power of minus 4. So 1.8 times 10 to the power of minus 4 newtons. So this over here is the horizontal vector. Notice that, well, we know the adjacent component. We also know the opposite component. So this means that we can use tan of theta. Remember, tan of theta is opposite over the adjacent. So this means that tan of theta will be opposite, which is 1.8 times 10 to the power of minus 4. Just one thing, not up to two significant figures. This value here was 1.74, so you're going to get a slightly different answer if you're using the more accurate version of the force up to more significance. I'm going to use the 1 up to 2 significant figures though, so 1.8 times 10 to the power minus 4, and then I'm going to divide that by the adjacent, which is 6.38. Actually, shall we just use 1.74 because I've just used the 1 which is up to two significant figures, so 1.74 times 10 to the power minus 4. This way I'm using this up to two significant figures and this up to two significant figures. So 6.38 times 10 to the power of minus 4, which means that theta, if we take the inverse tangent of this, will be equal to tan to the power of minus 1, or inverse tan, of 1.74 times 10 to the power of minus 4 divided by 6.38 times 10 to the power of minus 4. And if we plug that into a scientific calculator, just being quite careful with the brackets, we should get approximately equal to 15 degrees. So that's 15.25. Let's use two significant figures, which is 15 degrees. Please note that if you've used 1.8 here, you're going to get about 15.8, I believe, which is about 16 degrees. Okay, so that was quite a good question. Let's do another one. Okay guys, so the next question is from OCR Physics A from January 2013. The first part is to once again define the electric field strength at a point in space. So the electric field strength is just the force per unit charge, so it's the force per unit charge. The equation for it is that the electric field strength is force divided by charge. So on to the next one. Apart from the magnitudes of the electric field strength, state another difference between the electric field points between points B and C. Well, they're much further away from one another, which would mean that the field strength will be very different, but also the direction will be different because remember the field strength is actually a vector. If there's a positive charge here, the field lines will be emerging radially out. So this means that at point B, the field line will be pointing upwards, vertically upwards, and at point C, it will be horizontal and pointing to the left. So what we can write down over here, so the difference is simply the direction. For part 2, we need to determine the magnitude of the electric field at point C. Now notice that the distance from C to A is twice as much compared to from B to A. So this means that the electric field strength will be considerably lower. How much lower? Well, we know that the electric field strength is proportional to 1 over r squared. In other words, if we double the distance, we are going to get a decrease of a factor of 4. So the electric field will decrease by a factor of 4 compared to the value that it was on point B. And we're given that the electric field here is 8.0 times 10 to the 5 at point B, which means that at point C it will be 4 times lower. So if we just divide that value by 4, we're going to get 2 times 10 to the power of 5 newtons per coulomb. So moving on to part C, the simplest atom is that of the hydrogen, and that has 1 proton and 1 electron, and we have a little picture of this atom over here. Calculate the magnitude of the electrical force between them. Okay, well, the electrical force is given by the product of the two charges divided by 4 pi epsilon naught r squared. So the magnitude of the electrical force will be given by the magnitude of both of those charges. So it's going to be 1.6 times 10 to the power of minus 19 times 1.6 times 10 to the power of minus 19. And then we are going to divide that by 4 pi. Epsilon naught is 8.85 times 10 to the power of minus 12. And we're going to be careful not to forget to square the distance. So it's going to be 5.0 times 10 to the power of minus 11. All of this is squared. Inputting this into a scientific calculator, up to 2 significant figures, this will give us 9.2 times 10 to the power of minus 8 newtons. And for the last one, guys, what we need to do is we need to calculate the ratio between the electrical force and the gravitational force. Now, the gravitational force is given by minus gmm over r squared. And we can see I've calculated this over here by essentially using the value for the constant g, 6.67 times 10 to the power of minus 11, multiplying that by the mass of an electron, 9.11 times 10 to the power of minus 31. The mass of a proton is 1.67 times 10 to the power of minus 27. You can find both of those values in the OCR formula booklet. Dividing that by the distance squared, we're going to get 4.06 times 10 to the power of minus 47 newtons. So it's a tiny, tiny force. As soon as we divide those two numbers, remember a ratio is simply one number divided by the other. So in this case, the electrical force is 9.2 times 10 to the power of minus 8, and we calculated that here. The gravitational force is 4.06 times 10 to the power of minus 47, and we calculated that here. And when we divide those two numbers, we're going to get 2.3 times 10 to the power of 39. So remember, the electrical force is many orders of magnitude stronger than the gravitational force. Okay guys, on to the next one. This one is question 1 from the OCR Physics A paper from January 2011. Let's get started with this one. So we have the following circuit over here. We know that we have some parallel plates essentially between here, and the voltage is 2400 volts. Calculate the force acting on an electron. We also know the plate separation. So the electrical force is equal to the electric field strength multiplied by the charge, and the electric field strength, because there will be a uniform electric field between the plates, will be equal to V over D times the charge. Now V is equal to 2400 times by the charge, which is 1.6 times 10 to the power of minus 19. We're going to divide this expression by the distance, which is 9.4 millimeters. So it would be 9.4 times 10 to the power of minus 3. That's going to give us 4.09 times 10 to the power of minus 14 newtons. So part 3, what we need to do is calculate the speed of the electron when it reaches plate B. Okay, so we already know that the gain in kinetic energy is this many joules, so we can just use directly the kinetic energy formula. So all of this formula gain, all of this energy gained is transferred to kinetic energy, and the formula for that is a half mv squared. So just rearranging for the speed, we're going to get that the speed is equal to the square root of 2 times ek divided by m. So that'll be the square root of 2 times 3.84 times 10 to the power of minus 16, and we're going to be dividing that by the mass of the electron, which is available in the OCR Physics A formula booklet. So it's going to be 9.11 times 10 to the power of minus 31. Plugging in those two numbers, or those numbers, into our scientific calculator, we're going to get about 2.9 times 10 to the 7 meters per second. And the final question, the separation between the plates is doubled, but the PD across the plates is kept the same. Explain how this would affect your answer to the previous part. AII. Okay, so that's the gain in kinetic energy. Well, the gain in kinetic energy is given, so the gain in kinetic energy is, let's say that this is equal to delta KE, is going to be equal to the charge multiplied by the voltage. So it only depends on the voltage. So it only depends on V and the charge E. So therefore, there will be no change. So part 2, the radioactive nucleus emits an alpha particle. State the change of any to the graph in the figure, and then we need to explain our answer. We need to do two things. We need to state and also explain our answer. First off, the gradient, as we wrote up here, the gradient is equal to Q divided by 4 pi epsilon naught. As I've just written this over here in words, and if the charge decreases, so will the gradient. So this is literally what I've written down. The charge decreases. This is actually our explanation. That's 1 mark. Therefore, the gradient will decrease. Okay guys, part C, we have a negatively charged droplet of oil is held stationary between two horizontal plates. There are two forces in balance here. One is the electrical force, the other one is the weight. We're given that the droplet is spherical and has a certain radius, 1.27 times 10 to the power of minus 6, and we're given also the density of the oil. Show that the magnitude of the charge on the droplet is about 1.1 times 10 to the power of minus 18. So the basic idea here is that the weight, which is m times g, is equal to the electrical force. Because we know that the potential difference is 1.5 kilovolts and we know the separation, this means that we can figure out the electric field using V over D. And once we know that, we will know that the electrical force is the electric field is the force per unit charge, like so. And the idea here is that mg will give us the force, and once we have the force, we can figure out the charge using the fact that Q will be equal to F times D divided by the potential difference. Okay, well, let's start off by just figuring out the force first of all. So we need to figure out the mass. Because we're given the density, I'm going to use the fact that density is mass over volume, which means that mass is equal to volume times density. So V times rho, where rho is the density, times G is equal to F. Now the volume of a sphere is 4/3 pi r cubed times the density times G is equal to the force. Well, this will be equal to 4/3 pi r cubed. So the radius is equal to 1.27 times 10 to the power of minus 6, multiply that by the density, which is 950, and multiply that by G, which is 9.81, and we are going to get a value for the weight being 8.15 times 10 to the power of minus 15. So that's 8.15 times 10 to the power of minus 15 kilograms. Now that we know that, we can directly figure out the charge. So the charge is the force times the distance. So the force is 8.15 times 10 to the power of minus 15 multiplied by 2.1 centimeters. That's the separation between the plates. So 2.1 times 10 to the power of minus 2. And then we're going to divide that by the voltage, which is 1.5 kilovolts as shown here. So it'd be 1.5 times 10 to the 3. Now all we need to do is put that into a scientific calculator and find the charge, which will be equal to about 1.1 times 10 to the power of minus 18 coulombs. Now that we have the charge, we can also calculate the number of excess electrons. All we need to do is really take that number, 1.1 times 10 to the power of minus 18, divided by the electron charge, which is 1.6 times 10 to the power of minus 19. And if we put that into a scientific calculator, we are going to get, well, it needs to be a whole integer, so we're going to get 7 excess electrons. Okay folks, well, hopefully you've enjoyed this video and most importantly you found this very useful. Well done for solving so many questions on electric fields, and if you've enjoyed this video, please consider subscribing.